Hello everyone, myself Prayag Patel, working as assistant professor in IT ICT department of LJ Institute of Engineering and Technology. Now in today's video lecture, I will discuss about the graph traversing. Graph traversing means you can move in a graph from a root node or any node to remaining node. It's considered as a graph traversing. In graph traversing, there are two techniques for graph traversing. Consider the two algorithm or two technique for graph traversing. First one is breadth first search and second technique consider as a depth first search. So here consider the two technique for traversing a graph. Here consider the one by one technique. First we consider breadth first search algorithm. Now in first understand how breadth first search algorithm will work. Breadth first search or BFS is a graph traversing algorithm. Here consider it is used for traversing or searching a graph in a systematic fashion or systematic manner. BFS use a strategy that search in the graph in breadth first search manner whenever possible. Means you can search the element by level as consider as a breadth by breadth. So here consider searching of element or node in a level by level manner. Now consider the which data structure used for the breadth first search. Then consider the Q data structure is used to implement the breadth first search algorithm. Now consider one example for understanding the breadth first search algorithm. Here consider the example traversing the following graph using the breadth first search technique. Here given graph, in graph there are many nodes R, S, T, U, V, W, X, Y. In this graph many edges are there. Then you want to search the element from this graph. So here initially consider starting point. Now in BFS you can consider any node as a starting point. If in example given data like node number S consider as a starting node, then consider the node S as a starting node. In this example we consider the node number S as a starting node. So here consider the first step number 1. For all the vertices, you accept the source vertex S of the graph. We initialize color of U equal to white. So here consider the for each vertex U, means here consider the vertex as a R, S, T, U, then V, W, X, Y. This all consider as a vertices. So this all vertices consider as a U. Then for each and every U, you can perform the following operations. First consider the color of U equal to white, means initially for each and every node consider the color of each and every node equal to white. Here remember that initially all the nodes color as a white, then first time you visit that node then color consider as a gray, then after this color make a black color. So here consider this consider as a white color for each and every node. Now consider the Q. Here consider one Q. In Q we represent the one by one node. Now consider the next as a pi of U equal to nil. Now what is the pi and why we use the pi? Pi function used for the data or consider the root node or parent node of your particular node. For example, we consider the initially all the nodes are not connected. So parent of in your tree, because this is considered as your graph. But when you represent this graph in a tree, then consider the any node as a parent node or root node. So in tree form, you consider the parent of each and every node. So initially each and every node considered as a no parent or no set any parent. So here consider initially pi of U equal to nil, means here consider node U as a R, S, T, U, V, W, X, Y. For all the node, parent node is not set. So here consider pi of U equal to nil. Now consider the next as a D of U equal to infinity. Here consider D of U means here consider node distance. So here consider root node as a 0 distance, then next level consider as a level 1 or distance 1, then next level consider distance 2, then next level consider distance 3, like this. So here first you consider initially each and every node distance equal to infinity. When we move the node or traverse the graph, then we can decide the distance. So d of u represent the distance of the node. So here consider d of u equal to infinity for each and every node initially. Now consider the next. Here S node consider distance 0, remaining all node distance consider as a infinitive because S consider as a initial node. Now for source vertex S, here consider S node. For source vertex S, we initialize the variables S. Color of S equal to gray. Initially color of S equal to white, but when we start the traversing of the graph from the root node from the node number S, then consider the color of the S node as a gray. Then consider next pi of S equal to nil. Pi of S means parent of the node S consider as a nil because S consider as a first node, and in a tree first node consider as a root node. So root node parent node equal to null. So in here consider pi of S equal to null. Now consider d of S equal to 0. D of S means distance from the root node or how many level are there. So here initially consider the S as a root node. So distance of S equal to 0. And insert the Q. In the Q, insert the one element consider as a element S because here S consider as a starting node. Which node are inserted? One by one each and every node are inserted in a Q. Okay. So simply we can say that from the starting node, consider the distance of the starting node equal to 0, remaining all node distance equal to infinitive, and color of all the nodes are white initially. Then one by one node, when we select this node, then color consider as a gray. Okay. Now consider the step number 2. In step number 2, we consider the first step as a DQ vertex S from the QQ. So here consider first when we insert the element S in a Q, then after we consider S node in a Q, then remove the first node. Here DQ operation means delete from the Q. Remember this operation DQ. DQ means delete from the Q. So here we delete the first node in the Q. So only one node in a Q S. So we remove the S from the Q. And what we can do here after removing the node S from the Q, insert the neighbor of the node S into the Q. So here consider the neighbor like for all adjacent white vertices V. Here consider initially only S node as a gray color, remaining R and W as a white color. So here consider the all white vertices or adjacent vertices of S, means consider as a R and W. Of vertices S, we do first consider color of V equal to gray. Here consider V means we consider as a neighbor of S, adjacent of S. So here consider V as a R and W. So here consider the color of R equal to gray, then color of W equal to gray. Now D of V equal to, here consider D of S plus 1. So because here consider D of S as a parent node and R and W consider as a child node. So D of V equal to 0 plus 1 equal to 1. So here consider the distance for node R and distance for node W consider as a 1 in this node. So here consider third step, pi of V equal to S. So pi of V means R and W consider as a V. So here consider pi of R equal to S and pi of W equal to S, means pi of R or pi of W means parent of R and parent of W consider as a V. So here consider the tree as a S as a root node, and here consider two child, one child is R and another child is W. Now consider the last step, EQ. Here EQ means consider the insert in a Q. DQ and EQ, here two functions are there. DQ for delete the node from the Q and EQ for the insert the node in a Q. So here consider EQ all the adjacent white vertices of S in a Q. So here consider S adjacent vertices is R and W. So insert the R and W in a Q. See in this figure. Now consider the next step, step number 3. In step number 3, you can perform the sum operation. But before that, we remove the here one node number S. So if we remove the node number S, then consider the color of the node number S as a black, because initially all the node are white. When we visit this node, then consider visit this node and insert this node into the queue, then consider color as a gray. When we remove the node from the queue and consider the insert of its adjacent node in a queue, then consider the color as a black. So here consider the step number 2 as a this. Now consider step number 3. So here consider W. In previous case we see that W as a first element in a queue. So we remove the W from the queue and insert the neighbor of the W in a queue. So here we consider first step as a delete from the queue. So here consider this graph and first element is delete vertex W from the queue. Then consider the for all adjacent white vertices V vertices means neighbor of the W. So here consider the neighbor of the W as a T and X. So for T and X perform the following for operation. First, color of V equal to gray means color of T and color of X equal to gray. Then distance consider as a parent node distance plus 1. So here consider parent node as a W. So W distance plus 1 means distance considered for T and X equal to 2. So here consider distance for both the node equal to 2. Now pi of V means parent of node T and parent of node X consider as a W. So here consider this formula, and for the step is equip all the adjacent white vertices of W in the queue. So here we remove the W from the queue, then consider R is already in a queue. Now insert two node or two vertices of the node W or adjacent of the node W is a T and X. So insert the T and X in a queue. So consider this is as a inserted element. Now color of W consider as a black, means here we can say that color for the node W equal to black because we remove the node W from the queue and process for the node W is done. So here consider this is as a third step. Now consider the next step as a step number 4. In step number 4, consider DQ vertex R from the QQ. So here consider first element from the queue. In previous step we have seen that here in queue first element is R. So remove the R element from the queue and consider the next element. So here consider next element as a element T. So here consider remove element consider as a R. So DQ vertex R from the queue. Now consider the neighbor of the vertex R. So here neighbor of the vertex R consider as a V. So consider the for node V we perform the following operation. First operation is color of V equal to gray. Here see in this figure, here consider color for the node V equal to gray. Now second step, D of V equal to D of R plus 1. So here consider D of R means 1 plus 1 because your V node consider the child of the R node. So R consider as a parent for V. So we consider 1 plus 1 equal to 2 for the distance of node V. Now consider the parent of the node V. Here consider parent of the node V equal to R. So consider pi of V equal to R. And last operation, insert all the neighbor of the node R into the queue. So we can say that in queue all the adjacent white vertices of R in a queue. So here consider only one vertices and vertices name is V. So we insert the V element in a queue. Now consider the color of the node R equal to black because neighbor of the node R is complete. So here consider color of the node R equal to black. Now consider the next process or next step, step number 5. In step number 5, we remove the first element from the queue. In our previous queue, T considered as a first element in a queue. So we remove the element T from the queue. So here consider delete vertex T from the queue. So consider the neighbor of the vertex T for all the adjacent white vertices V. Means we can consider neighbor of the T consider as a only U. So here consider vertices V as a vertex U of vertex T. We do following step. First step is color of V equal to gray. So here consider node number U color equal to gray. Now consider the d of v equal to d of t plus 1. D of t means distance of the t or level of the node t equal to 2. 2 plus 1 equal to 3. Now consider the pi of v equal to t. Here pi of v means, consider here pi of v means distance from the or parent of the node t. So here parent of the node you consider as a t. So consider pi of v equal to t. And next step is insert the neighbor or white vertices of the particular node, consider as a t. So here in Q all the adjacent white vertices of t in a QQ. So here consider this is considered as a fourth step. Now after performing this operation, node t become a black node because parent or child of the node t are done or executed. So here consider color of the t equal to black. Now consider the first node in a queue. In this queue consider the x, v and u. Three nodes are there. So consider the first node from these two, consider as a x. So in step number 6, initially we consider the first node from the queue as a vertex x. So first operation, dq vertex x from the QQ. So here we remove the x from the queue. Now after that we consider the neighbor of the node x. So here neighbor of the node x consider as a y. So here consider y as a vertex v. Okay. Now perform the following operation for this vertex. Here first consider color of v equal to gray, means color of y equal to gray. Second step, d of v equal to d of x plus 1. Here consider d of x equal to 2. Then 2 plus 1 consider as a 3. So here consider d of v equal to d of x plus 1, means 2 plus 1 equal to 3. Now consider the next step, step number 3, pi of v equal to x. Here consider pi of v means parent node of particular v node. So here parent node of v node consider as a v node, consider as a y. So parent of y consider as a x. Now consider the fourth step. In Q all the adjacent white vertices of x in a Q. So here consider adjacent vertices of Q as a which node, which adjacent vertices consider here. So here consider the adjacent of x consider as a y. So insert the element y in a Q. So in Q we see that v, u and y, three elements are there. Now process for the x node is done. So consider the color of the x node equal to black. Now consider the first element from the Q. In Q there are three elements v, u and y. Out of these three elements, consider the first element and remove the first element from the Q. So here consider the first element as a y. In here we remove the element v, because first element consider as a v, second element consider as a u and third element consider as a y. So first we remove the v, means we can say that the dq vertex v from the Q. So here in Q only two elements remaining, u and y. Now consider the one by one process for the particular node v. There are no adjacent white vertices to vertex v. We consider in each and every case of previous case, we consider the adjacent vertex of particular vertex v, and we consider this node as a white node, then we can perform the sum operation. But in the node v, we consider there are no adjacent white vertices. So here consider no any operation is performed for that. But here consider the color of the initially color of the vertex v as a gray. So here we perform the operation, no any adjacent node are available for that node. Then consider the color of v equal to black. Now consider the next step. Here in previous step consider the situation of Q. In Q there are two elements u and y. But here consider the first element in Q as a u. So here consider the u as a first element of the Q. So consider and remove the first element from the Q. Means we can say that dq the vertex u from the Q. So here consider the u as your node. Now consider the neighbor of the node u. But here no any white vertices remain for the node u or adjacent of the node u. So we can say that there are no any adjacent white vertices to vertex u. So here consider the no any operation is done. Only we can say that color of the node u consider as a black, because for the node u all the operation is performed. Now consider the next step. In next step we consider first situation of q. In q only one node are there, node number y. So here we perform the operation for the node number y. Here in node number y we remove the y node from the q, then q situation is empty q. So first operation is dig q vertex y from the q. Then here consider the neighbor of the vertex y, and here no any neighbor or white vertices of the node y. So we can say that the no any adjacent white vertices available for the node y. So here color of the node y consider as a black, because we perform the all the operation for node y. Now consider the here consider for all the node we perform the operation, means since all the vertices have turned black and the q has got empty, so we stop the process. So here consider visit each and every node and consider the situation of q as a empty q. So we stop the process of the execution of the BFS. Now consider the BFS tree. BFS tree means breadth first search tree. In breadth first search tree we consider the our given graph. Now from the given graph we perform or write the some value in each and every node for r, s, t, u, v, w, x, y. We write the some value. So here consider the value consider as a level. So in tree initially consider as a level 0, then consider level 1, then consider level 2, then level 3, like this. So here initially consider the s as a root node, because we start the process from the node number s. So here consider s as a root node. Now consider the 0 level as a level s. Now consider the 1 level, means here in this graph consider the value 1 in which node. Here consider node r and node w consider as a value 1. So here we consider next node as a w and next node consider as a r. We can also write the first r then w, both the case are possible. So here we first write w then r. Now consider the next node as a child of the w. So here child of the w consider as a next level, means level 2 from the w, means consider node t and node x in this graph. So consider the node t is a left child of w, and next consider the node x as a next child of the w. So here consider this is a tree. Now consider the next. Here consider next level 2 node as a node v from the node r. So here consider 2 for 3 position t, x and y. So here consider the child of r as a v. Now here consider the s as a 0 level, wr as a 1 level, t, x and v as a 2 level. Now consider the level 3. Here in node t2 any node is possible. Here yes, one node is possible from t to u. So here consider t to u as your next node. Now consider the next node as a x to y. So here consider this is a final tree or final BFS tree for the given graph. So here consider s as a level 0, wr as a level 1, t, x and v as a level 2 and u, y consider as a level 3. Now consider the sequence of the BFS tree. In sequence of the BFS tree, we write the some sequence or order of the node, in which sequence you visit the node. So here sequence consider as a S, W, R, T, X, V, level by level. So here consider T, X, V, then U and Y. Also possible the some another order here. Now consider the next step is here consider the tree edge and back edge. Here consider the tree edge and back edge. Now tree edge means in which sequence we follow the traversing a graph is considered as a tree edge. So here solid line considered as a tree edge in this tree. Now consider the cross, or here consider cross as a dotted line. So here which edge are not covered in a tree but given in a graph. In graph there are two edges are there from T to X. and from U to Y are available in a graph, but in a tree we not write or define this node or this edges is considered as a cross edges. So represent this cross edges here T to X, then another cross edges as U to Y, then consider another cross as U to X or X to U. So consider this dotted line as a cross edges and solid line considered as a tree edges. So in BFS there are two type of edges available in a BFS tree or BFS forest. Now consider the algorithm for the breadth first search technique. Here consider the same example or same figure for understanding the BFS algorithm. Here consider the first as a name of the algorithm and name of the algorithm as a BFS, argument considered as a G and S. So here G means given graph and S considered as a starting point. For each vertex U belongs to G dot V minus S, means for each and every element consider as a element U, which can consider as a node of the given graph. G dot V means node of the graph or vertices of the given graph, minus S because here consider S because here we consider the S as a starting point. So consider the G dot V minus S means remove the starting point from the remaining all nodes. So consider the next operation as a color of U equal to white because initially we consider the each and every node color equal to white, not only S color equal to white, remaining all node consider color equal to white. Then d of U equal to infinitive means distance from the your root node to your particular node consider initially as an infinitive. Then consider the pi of U equal to nil means parent of your node consider as a nil because initially no any node consider in a tree. So initially no any parent node are set. So consider pi of U equal to nil. Now after this means these three green color line consider in a for loop. After completion of for loop consider the next line as a color of S equal to gray. Here consider S as a starting node. So consider the color of the S node equal to gray because this is considered our current node. Now d of S equal to 0 because distance of the root node consider as a 0. Now consider the pi of S equal to nil because root node parent node consider as a nil. So pi of S equal to nil. Now consider the Q equal to empty. Here consider the empty set or phi means initially in Q no any element are there. So consider Q equal to phi. Now consider the next step ENQS means here ENQ means insert in a Q. We already discussed in this example. Consider the ENQ function for insert the particular element in a Q. So here consider Q as a name of the Q and S consider as an argument which can be inserted in a Q. So here consider the first element S insert in a Q. So see in this figure initially root node value equal to 0, S value equal to 0, remaining all value consider as a infinitive, color of the remaining all element as a white and color of the S node as a gray. And consider the situation of Q as a only one node in a Q is S. Now consider the next step of the algorithm. In next step of algorithm, consider the same figure here. We perform the sum operation while Q is not empty too. Here please consider as a continuous algorithm. While Q is not empty means whenever the element is present in a Q, then we perform this while loop for performing sum operation. So here consider U equal to dqq. Here dq is another function for delete the node from the Q. So here consider dq as a first operation and consider remove element from the Q as a U. So in this case we remove the S element from the Q, then S consider as a U. Now for each V adjacent to U2 means here consider the V as a adjacent node of the U. So here consider the S node as a remove node from the Q. So S consider as a U. So neighbor of the U consider as a V. So here consider R and W as a V. So adjacent of U consider as a R and W. For each adjacent here we perform sum operation. First, if color of V equal to white, then means we check neighbor of the U node means node V color equal to white. Yes, then we perform the operation. So here consider color of V equal to gray. So here consider color of neighbor of S equal to R. So R color equal to white, yes, then we consider color of R equal to gray or color of W equal to gray. Now consider D of V equal to D of U plus 1. So here consider distance of your neighbor node R equal to 0 plus 1, means distance of U equal to distance of S. So 0 plus 1 equal to 1. Then pi of V equal to U, means parent of your child node. So here parent of node R consider as a S. So parent of node V consider as a U. So here consider last operation is ENQQV, means insert your neighbor node, means you perform the operation for node S, then remove the S from the Q, then after insert the neighbor of the node S in a Q. So neighbor consider as a W and R. So in second figure we see that we consider distance as a 1 1 for the node R and W, color consider as a gray for node R and W, and insert the node R and W in a Q. So here consider this step. Now last consider color of U equal to black, because we perform the operation for the node U, means consider the node S as a node U. So color of the node S consider as a black. So this is considered as a BFS algorithm, and in today's video lecture I understand about the example of the BFS and algorithm of the BFS. Thank you for watching this video.